So on to example 4. This time we're looking at the distribution for a proportion. And we have here a distribution for the proportion. Why are we using a proportion? We remember that proportions are used when we're looking at qualitative data, where we're looking at, does this happen or not? And when we see a proportion, we're looking at here, the long-term average proportion of students passing Stat 101 exam is 70%. So you either pass or you don't. That's qualitative data, and the proportion of people passing as 70%. So if we're looking for the probability in a sample of 50 students this year that less than 65% will pass, so this is from a sample of 50, what we're looking for here is the distribution of the sample proportion. And we can use the binomial distribution here because clearly you can pass or not, or we can use the central limit theorem and the normal distribution, and we're going to do both. So if we look at the binomial distribution, we know that in a sample of 50 students, the sample proportion will be less than 65% when x is less than 32, less than or equal to 32. In fact, you'll note that 65% of 50 is in fact 32.5, but because binomial is a discrete distribution, we can't have 32.5 people passing, so we have x less than or equal to 32. And if we use binom dist function in Excel with 32 for the probability of 32 or fewer, as we did with our previous examples, the probability that x is less than or equal to 32, we've got 32 or fewer with a mean of 50, x, in the binom dist we have the number of successes, we want the number of trials for the next one, the probability of success, which in this case is 0.7, and cumulative or 1. So that will give us 0.218. So use binom dist function to get that probability. Alternately, we can do this by using the central limit theorem as long as we know the sample size is large enough. So again here, if we're using the proportion of 0.7, that means in our sample of 50, we will be checking to see if the sample size is large enough by looking at n times p. That's 50 times 0.7, which is 35, so that's definitely bigger than 5, and n times q, and that will be 50 times by 0.3, and that's equal to 15. So they're both bigger than 5, so our sample is large enough. Now p hat, remember the notation p hat is for the sample proportion, and this is from a sample of 50, and we're using 0.7. So from a normal distribution here, where we're looking at the mean value, and that means the mean value is n times p, that's 0.7 times by the... We leave it as a proportion, so we're using the proportion here for the mean. Now we need to find the standard deviation. So remember, the standard deviation is calculated for the proportion by taking the square root of p times 1 minus p divided by the sample size. So our standard deviation for the proportion is given by 0.7 times by 0.3 divided by 50 and the square root of all of that. Now that comes out to be 0.0705, the square root of 0.0042 if you do this on your calculator or Excel, and that comes out as 0.0648. I think I said something stupid there. 0.0648. So inside of our Excel function, now we're going to be using the proportion for the mean of 0.7. The standard deviation is 0.0648 because that's the standard error value. And of course, if we're looking for the proportion to be smaller than 0.65, it means that we'll use normdist, N-O-R-M-D-I-S-T. The x value we required there is 0.65. We have the mean of 0.7, and the standard deviation given by that standard error measure, 0.0648, and 1 for cumulative. So using norm dist, that will give us a probability of 0.2202. And that's the same as the previous method to 2 decimal places, so we're getting the same probability to 2 decimal places using that approximation. So that's using 2 methods to calculate the probability that X proportion here of smaller than 0.65. So that's the end of example 4.